I could smuggle myself in, but
You pull off such shenanigans, you'll be facing the doctor at the Delhi airport again for some vaccination shot.
Don't threat.
So, shall we get started then? So, welcome to the last day of this workshop. So, we have three speakers, and our first speaker is Jorge Kurchan, who will talk about a world with a docile clock. Well, please, Jorge.
okay, thank you very much. So I'm going to go quickly. I'm going to talk about two different aspects of glasses, mainly the first, that one is that time flow is easily modified. The meaning, and this is the meaning of this picture, the film is always the same, but the rate at which it is projected is easily changed. And I'm going to try to convince you that, at least for my taste, this is almost the essence of glassiness. And second is multi-thermalization, of which I'm going to go quicker. So I don't have to tell you here that a glass does, roughly this. With temperature or something else, it goes up, and perhaps it diverges at some temperature that is non-zero. This could be well, it's a typical time scale. So the first, perhaps not even the first, if Jeppe is going to talk about similar subjects, he knows the prehistory of this subject much better than I honestly don't know it very much, the prehistory. But for me, the first indication of this kind of thing where evolution is modified very easily by doing something, in this case changing temperature, is what is called time-temperature superposition, which is just telling you that these guys, this is for polymers, but expected something, some property, to simply scale its time, stretch its time very much with temperature. Here we are on the liquid side. So, and this then received a lot of attention in the context of mode coupling, which there's nothing special about mode coupling here, but it also has this property. This was, at the time, I don't know if people realized that this was the tip of an iceberg. So let me tell you how we got there, we meaning a few people, to this question of having your projector and projecting at very variable speeds. So you don't have to pay attention to any of the details here, but you define the correlation and the response of a system. And as you know, these things tend to have a fast part into a plateau and then a very slow part. And then you write some equations, please don't read them. And what you find is that there comes a time where you have this Q contains all the physical correlations and responses. The only thing I want you to see here is that there is a moment where you drop this derivative with the argument that everything is slow, and so a derivative gives you a very small number, and you think, okay, I can solve these equations without this derivative, and you can, but something strange happens, is that this equation admits a solution for the time dependence of correlation, but also any stretching of these solutions. So it's as if I give you the celluloid, the film of the film, and I don't tell you at which speed I am projecting it. The facts are concatenated this way. I'm not going to quote once again Casablanca, because I always do, and I'm a bit tired of doing it. But so they give you the film, but not the speed, even nonlinear speed, which could change. And this is a problem of having done this approximation, which becomes exact. So something very bizarre happens. A quasi-symmetry arises in your problem. to the best of my knowledge, this was discovered by Sompolinski and Zipelius around 82. And what are these equations? Well, these equations could be the exact equations for all these models like p-spin and such, but more modernly, perhaps more convincingly, they are also the equations of a liquid in large dimensions, which you can solve exactly and give you this sort of equation. Okay, so this is a surprise, and at the time, people were sort of more angry than anything at this fact because it made the solution harder. Okay, so this is the quasi-symmetry that glasses have, and we have evidence that they do have it. It's not only a question of the model. It's the fact that you're given the film, and that's a hard part, the part that is difficult to change, but the speed at which it is projected is very easily modified. And so I made these to clarify, but they tell me they don't. You have the film, and if you're comparing parts of the films, so this is one scene, this is another, and red happens to be close to blue, and red happens to be close to blue, you don't need times, no? So, and you can get rid of the times just by comparing things in the film to other things in the film without making any allusion to time, which is the same as saying that you write one correlation in terms of another. Or you can compare 3 points of the films and do correlations like this in a triangle. In this scene, there is this gentleman. In this scene, there is this gentleman in this scene. And you just relate them at the time when this was here and that. So if you eliminate times, you are simply expressing things where times have gone as parameters. And all the changes you do by passing your film quicker or slower disappear. For example, the most celebrated case is when you plot a correlation against the integrated response in the interval. Times are gone, and this is something well known. Okay, so let me tell you examples where this appears and you confirm that it's the way it works. I told you already this case, a very famous case that was noted by Strauch in, I don't know, many, many years ago, is that if you take a ruler and you do aging of the ruler, so you stretch it and see how it creeps, it ages, so these are curves for different times. But if you take your ruler and every weekend you do this to the ruler, then it stays young. It does exactly the same, but the time scale at which it does it is that of a younger system. Younger systems have the same correlations, but that do the same things, but faster, and then progressively things become slower. This is aging, but you can stop aging very easily just by shearing your plastic ruler. And this has been checked, but this, I think, was discovered by him many, many decades ago. Thing that we recently did, and now the authors are invisible, but there is Ludovic here, is to look at the programs that Ludovic and co-workers had developed for super accelerating the dynamics of classes. And we tried to check if it was an instance of the same film, but just that, thanks to Ludovic's magic, was passed faster. There was, if you didn't know the theory, you would have no reason to believe that that was going to be the case, but it is. And we checked, these are, what we do is we plot a correlation against another one. So it's like comparing parts of a film without, so when you plot a correlation, a K mode against another K mode, time is gone. And we do it with the ordinary program and a variant of Ludovic's, which goes 100 times faster. It can go much faster, but we stayed at 100. And you see that you get that the plots are straight one on top of the other, which means that you are indeed watching the same film, only passed 100 times faster. This is quite anti-intuitive. It means that whatever magic this swap program is doing, it changes the shortish times, but somehow it's as if you were going through the same landscape, but with a bike instead of walking, something like that. This is in the glass? This is within the liquid as you are approaching the glass phase. Not aging. It could have been done aging, but we didn't. So it's in the liquid where everything was controlled. We were close enough to the transition so that it was interesting. We used the program at half power, because only 100 times, because we wanted to compare slow with slow, because otherwise, and we cannot have slow and 100 times slower, so that's what we did. But it's quite remarkable, and
just one question, because of course it's reminiscence of the Markov property. So is this, if you have a Markov process, do you have automatic?
You mean a Markov process where you do the same jumps with the same probability, but I don't tell you at which rate?
Exactly. Do you have the same property? Is it a consequence of a
It would be very nice to go deep and find it at the inside of the workings of the thing, but we don't have that kind of control. It sort of emerges and then you don't, but it has to be kind of like this.
Sorry, just say again what you're comparing here.
One correlation against another. So position, and now I'm going to say it, of Humphrey Bogart against Ingrid Bergman, okay? So the film, no matter how fast you pass it,
Right.
when one is climbing to the airplane, the other one is down looking, no? This is a concomitant. So when you plot one correlation against another, time goes away. Mm-hmm. And now what we find is that the program that goes 100 times faster keeps these concomitancies. So things happen at a different pace, but the same things happen.
Okay. So the 3 frames are 3 different temperatures where you.
That could be more rich. Here it's in this case, it is one same temperature, simple program, whatever, Monte Carlo, elaborated program, and you are comparing correlations with correlations, and you see that they do the same thing. And then this one is very surprising. It's a lovely paper by Tommaso Rizzo, super technical, where he calculates the passage from one deep part to another deep part in a mean field model. It's super difficult. And so he says, okay, I start at this temperature and finish at a final time there, in that other place. And then he tries different fixed times at which you are asking that the system arrives. And you discover that the correlations follow the same history, only stretched in times. He found that, which again is super surprising. And it takes a while to figure out how this could even be possible. It's exactly the contrary of jumping a barrier. It's the same film that arranges itself to pass at the appropriate speed so that you get there at the time that you asked. Okay, and then there is a lot of developments that the group of Jeppe has done. Sorry, what's the name of your young collaborator who's now in Paris? Aude. She showed us also the latest she did. It's quite amazing. I'm going to, and 2 things will happen there. One is a lot of more complicated and elaborated situations, and also a historical part, because I told you the theoretical side that how we got there, but there seems to be Ramaswamy, etc., long before at a phenomenological level where having this intuitively, so that's quite remarkable. But I'm not very good for that. This is things that these gentlemen did long ago. They looked at the fluctuations. The plural, le masculin. Okay. So if you have a soft mode, you expect that it's easy to change, but you also expect that fluctuations in that direction are big. And they had this very natural idea to look in a, let's say, in a plot of correlation against correlation. The soft mode would be where you are at given times on this line. just look at it superficially. The only thing they wanted to show here, and this is in a true model of spin glass, that you see the fluctuations are along this line. Well, it means that if you project with a shaky hand, the fluctuations will go not in the direction of changing the film, but on making the speed fluctuate. It's a very, very natural idea, and these papers are very nice, and they were largely unnoticed. Okay, so I think multi-thermalization, I'm going to be super quick. I don't want to particularly talk a lot about this, but one thing that appears in solutions and to a certain degree in simulations of these systems is that you get that the system behaves as if at different time scales it were at different temperatures. And you can cook up a solution in this way. So you have nested time scales, and at these time scales, it behaves as if it were at different temperatures, which you tell by looking at fluctuation dissipation. And so multi-thermalization is this situation where the system, and you have a kind of Gibbs measure for that. This is a horrible formula that has many levels in the history of spin glasses for different things. It's a Gibbs measure at a temperature nested inside one at a different nested and so on. And this thing produces this other thing, just curiosity. Why do I tell you, and sorry, and this was fluctuation dissipation. You probably know these plots. And this is a vintage picture of that we did for 30 years ago with the resources of the day, and how you measure it. But in any case, you have this situation. Why am I telling you this fact that is different? In a second, how much do I have? Oh, good, excellent. Okay, so, yes, yes. But, so two things. The reparametrization softness, which means you can pass the film and change very easily the speed at which you're doing it, and you have multi-thermalization. The second one, as I will convince you, I hope, in a second, is hinges on the first one. So these are not independent facts. Okay, so small parentheses. It's a very fascinating story for another day. SYK. SYK is this is just for curiosity, is a model that is essentially a spin glass, but quantum, and these guys are fermions. In this case, Majorana fermions, but it doesn't really matter. Any fermion will do. And this is a disordered J's like you are accustomed to in simple models of spin glasses. You want to solve the quantum mechanics of this. You get something in imaginary time. You get a time derivative, as I mentioned before. You say things are going slow here, so let me throw it away. And you discover that a time reparametrization softness emerges exactly the same way, exactly in the same way. But here you can do a bit more. These people who were doing this, Kitaev mainly, can write how much does it cost you to change your speed. So it's kind of like a sigma model. When you have something that is soft, you write a theory that only contains the soft thing. And this was done by Maldacena and Stanford, and they wrote this theory. And what is very interesting is that they, and everybody believes that this is a toy model for how a quantum theory gives you gravity. And gravity is the theory of the reparametrizations. So it's a lovely story that, just to tell you very quickly, that the same ideas appear in a field that has absolutely nothing to do, and technically in very, very much the same way. Okay, that's the end of the parentheses. Okay, so now I told you this sensitivity of the system to change its time scale, and I told you also that you have, at least analytically and to some extent numerically, for example, two temperatures with two different time scales. And now you have a problem, because you say, if I have two systems like this and I couple them, but the time scales don't match, then I can have a problem. I can have that this other temperature is going to, which is different, is going to live in the same overlap with the same time scale that this other system has, and it's a different temperature, and I want it only one temperature per time scale. That's the key of the thing. So it would mean that this scenario is fragile with respect to weakly coupling two systems. So if it's true separately, when I couple them, it becomes not true. And that's very bad. But that's not what happens. What you can prove, and it's quite amazing, is that when you couple two systems, because timescales are very liable to be changed, the timescales stretch and contract, and so that each temperature occupies a different timescale. This seems absolutely like special pleading, but it is what happens. For those of you who like replicas, and I don't see anybody here, but normally there are many, this also happens with replicas. If you have two systems with one-step replica symmetry breaking and you couple them, you get a contradiction, because if the x's, for those who do replicas, are different, then you have a mismatch. What does the system do? It produces a two-step with the two x's separately. Well, formally, it is very similar. By the way, Parisi did not follow this step to go from one step to more steps. Just, it would have been a natural way. That was not the one he took. Anyway, so what I'm trying to say is that the possibility of having multi-thermalization hinges upon the fact that temperatures, timescales can readjust themselves very cheaply, even with a very tiny interaction. Okay, to recap. These are two central features, but to my mind, after all, what is a glass typically? What we say is that as you go down in temperature with a liquid, you have a dramatic slowing down with very little changing. Very little, usually people say a snapshot looks similar, but they should say more. They should say the film looks similar. You are watching actually the same dynamics happening at different speeds. So in fact, what we all say when we talk about glasses is that as we approach a slowing down that may be at the end of which there is a transition, maybe not, the fact is that you are essentially watching the same film at progressively slower and slower speeds. The only thing I'm adding to this, or that we are adding to this, is that this is much more true than simply that statement. You can change the rate by using the clever algorithm of Ludo. You can change it by doing all sorts of bizarre things that Jeppe does. You can change it in a lot of ways, and always the softest mode a glass has is its time evolution, its speed of evolution. And this is almost, well, and so how would one envisage a theory, an abstract theory for this kind of situation? Well, if one could have these abstract symmetries, the multi-thermalization part and the stretching of time, as your theory that contains only that, this would be the sigma model for glasses. People in field theory for SYK did it for SYK, and as I told you, obtained a theory which they call the toy version of gravity. So this was done, actually. So at this point, I stop so that his question comes after.
Are you saying something more than the system is Boltzmann statistics, and therefore all that I need to worry is about Metropolis-Steinstein switches, such that I accept a step if the energy goes down, and I accept a step with E to minus beta E if energy goes up. And the rate at which I do these steps depend on me, and it doesn't matter. So it's really, you need to have equilibrium, otherwise none of this will work.
Almost.
Almost, okay.
Almost. So it is quite true what you're saying, except that it has different temperatures in widely separate timescales. So it is as if the model were doing two of these detailed balance situations, one that is relatively fast for the fast processes and one that is immensely slower for it. But it is true that this kind of situation, except that it's multi-thermalized and not thermalized, for the rest, you're right. Okay. You're following that kind of path. And somehow, in the intricacies of Ludo's program, one should be able to see that this is what is happening. No. But it's not obvious at all, because, well, yes, because he does different rules, but which are the efficient motions is not the swap itself, it's some sort of funny combination. So, yes.
So I'm thinking about experiments in aging and how it fits with this picture. So my understanding is that if you take, for example, do temperature jumps in a molecular glass, little jumps, the material time assumption works out really well. The bigger the jumps are, the less well it works out. If you do a big up jump, it fails spectacularly. So how does that fit into this picture?
So the fact that for temperature jumps this works requires additional assumptions. So it could be that in a temperature jump, you're not only, it's so big that you're not only moving the projector, but you're moving Ingrid Bergman away from Humphrey Bogart. You see, and this is not inside the kind of scenario I'm saying. What is cheap is a time repair, but if you force it too much, you can do more cruel things to the system. So this.
All right. So if I go back to the Claudio Leticia picture.
Yes.
The soft modes are following this line, which, if I remember correctly, is a particular relation between the integrated response and the correlation. So that's the kind of symmetry breaking. So you There's a particular relation.
That particular relation that goes back to Itamar's question is fluctuation dissipation with an effective temperature. Okay? That one you respect. Right. But where in the line you are depends on the time where you arrive.
And those are your soft modes.
And those are your soft modes. So what you're seeing is that your projecting person has a shaky hand, and so at 4 p.m., where exactly the film is liable to change, but the film is always the same.
But if I want to think of a symmetry breaking, it's basically that relationship.
Exactly, yes, exactly. And what they did is, well, then they made assumptions, but what they did was without. It was just truly looking at a system, which the field theorists didn't do.
I guess I'm confused. I thought that the time reparametrization was for the aging dynamics, and we could understand you had some evidence for this and analogies, and we could understand this. Now, I think you're saying that it's also true for the equilibrium dynamics. So you would say the alpha relaxation that goes through pads and in the energy landscape has also time reparametrization?
Indeed.
It's so weird.
It's so weird, but I'm going to convince you quickly. Remember Goetz's derivation of the exponents of mode coupling? I'm sorry to remind you of bad moments of your life, but remember that. At a moment, he throws the time derivative away. And it's the beta regime. Yes. And but that, well, but it's in equilibrium. But it's within equilibrium.
Yes, but it's the beta regime.
It's a beta regime, and then the matching multiplicatively changes your alpha. So he already was finding this, and for him this was time-temperature superposition appearing in his context. But what I'm saying is that this was the tip of the iceberg. Then when we found that kind of thing in aging, we were not even thinking of this liquid part. But then at the end of many years, one realizes that this is true all along. And in fact, even the slowing down of a glass is that. That's my point. I mean, I'm not talking about what generates it, but what emerges, is a kind of reparametrization. So it's not only I show you the picture of a supercooled liquid, I show you the picture of a glass and you don't see the difference. I would say I show you a film of a supercooled liquid and a film of a glass and don't tell you how quickly I'm projecting and you don't see the difference. So it's a bit more.
And maybe in that case, the film actually doesn't end in the sense that that equilibrium is anyways very, very far.
It's very far. Maybe it's infinity. Maybe not. Yeah, we won't know that in this reincarnation.
You would have not an ending film, and you would just.
Yeah.
So this may or may not be related to what Gilles is asking. I mean, if I think about the dynamics at different temperatures, right? In fact, I can look at the film at whatever speed and tell that they are at different temperatures in terms of, for example, the heterogeneity of the dynamics. So where does that come into this?
One should see that. One should see precisely that. Because also heterogeneity is because they are something that is one step beyond, no? Because it's itself a fluctuation. What you're measuring is a fluctuation. And the fluctuations are the trembling of the hand. In fact, I believe that all the heterogeneities, including the famous paper of Giulio, Jean-Philippe, what's his name, experimentalist, Ladieu, etc., I think that could be written in terms of reparametrization. We've discussed this. Can I say something? I have 2 minutes to say.
You have time.
D5 for you. I do what you did many years ago of starting in equilibrium at different temperatures in the liquid phase, but instead of going to 0 temperature and looking at the inherent structure, I go to a decently low temperature where I'm sure I have a glass, but not so low that I don't see anything, okay? So I claim that starting from different points, after the quench you have aging, the subsequent aging dynamics will be reparametrized as a function of the temperature equilibrium at which you start. And then you can rephrase the concept exactly in those terms. This is plain.
So can I keep going on the fluctuations? So within the PSPIN or DMF... Sorry, I can speak louder. So within the PSPIN or DMFT or MCT, you can, in addition to the equations for correlations and response, you can also derive the equations for the fluctuations chi4. So those will not...
Nobody has.
Yeah. Well, the PSPIN you can, no?
Nobody has as far as
Or the chi4, we've looked at chi4, chi-t, all these things. The equations for those would not be time reparametrization.
You could in principle, but it's hard.
Because we know that
the
the shape is the same, but the amplitude is different, so it's not only the time in the fluctuations.
No, but because what you are measuring, it's not inconsistent. It's sort of, it's not only a time reparametrization, but you're looking at a fluctuation. The fluctuations grow with the softness, and that is not the quantity that is reparametrized, that is the amplitude of the fluctuation, which is consistently becoming higher. But it's roundabout, but it's not in contradiction. And you wrote that theory in terms of only H reparametrization function, and you could solve it, you would be able to say exactly how these fluctuations of H are driving the
all the higher ties are driven by the same. I'm convinced that this is the explained everything.
Everything.
So our next speaker is Jeppe Dyre from Copenhagen.
Hello, can everybody hear me? No. No? Put it closer maybe. Okay, so I'm going to tell a lot of the same story, but in a different perspective that Jorge already told. Let me start by thanking the organizers for putting together such a wonderful meeting here. I have learned a lot, and I've also learned that mean field theory is still alive and kicking, which is good for mean field theory. So.
A little hard to hear you. Actually, you should put it up.
Yeah, but someone should do it.
Closer to the mouth.
I can do it for you, yes. Okay, so this is what the chair is good for. Do you allow?
Yeah.
Okay.
Okay, is it better?
They should do something there. They should increase.
Here, this is the easiest way. This is what I did yesterday. So I'm going to put this here. Can you try it now? The mic is not working.
Okay, that explains everything.
Yeah. In electrical engineering, before you start repairing something, make sure that the device is plugged in. That's the first thing you learn, before you even start sort of opening the case. Shall we try it here again?
Yeah.
Speak?
It's better now? No?
No. So you have to fix it.
Okay, so better? No?
No. Not too much. Can you speak now?
Yeah, better now? Okay. Sorry about this. This is the group as it looked some years ago. It's not quite as large anymore. And I will present some experiments that we have been doing recently and also some computer simulations. So let's just start by looking at, and the phenomenon is physical aging, which is basically the process where an out of equilibrium system equilibrates. And we always define the glass as any out of equilibrium version of the supercooled liquid. That's our definition. So these are data by Lisa and Christine. This is our setup where we have basically just a capacitor measuring dielectric signal and 50 micron liquid here. These are very long experiments on glycerol published some years ago. So this is, I think, something like 3 months of experiments. And what we do is that we change temperature and then we equilibrate, and then we change temperature up and down in different ways. And you can see the measured signal here. In this case, it's a very low frequency dielectric loss for historical reasons. Nowadays, we usually measure at 100 kilohertz, the real part, but this is the imaginary part at much lower frequency. But it doesn't matter. We just measure something, right, that we can measure accurately. And then basically you see that when you jump down here to 176, the measured signal eventually equilibrates. And this is what we want to understand. How is this process actually taking place? Here we plot the same data as function of log time. This was linear time after the initiation of the jump. And of course we end up in equilibrium. This is I think the lowest jump to the lowest temperature and so on, different jumps, and they end up equilibrating depending on what is the final temperature. The next thing we do is we introduce a normalized relaxation function. So you basically normalize this so that it starts in unity. And we cannot see this start because it's too rapid in our experiment. So that's why we start here. So these are the normalized relaxation functions. And what you see immediately, and you can see it already here, is that for jump to the same temperature, they look quite different. If this was a linear response, any jump to the same temperature and the normalized function would give the same function. But you can see they're quite different. You can see it here in the shape. So this is a highly nonlinear phenomenon, even for rather small jumps like 1 or 2 Kelvin, 1 or 2%. And the question is, how can we understand that? And the answer was provided a long time ago by an engineer at Ford Motor Company at the name of Narayanaswamy. And he published in the Journal of American Ceramic Society what's now regarded as a groundbreaking paper. He was trained in India, as far as I know, in mechanical engineering in the 60s. And he really didn't have an academic career at all, so it's difficult to find out, and I never met him. But basically, what he did is he took some intuition from rheology and transformed it into this field. And I like to picture this flexibility of time with this picture. So the fundamental postulate in his language would be that all these different normalized relaxation functions are determined by a unique function phi, which is the same for all jumps, as function of some variable called the material time. And then, of course, we have shifted the problem to understanding the material time. So this function phi is the same for all jumps, and this actually means that if we reformulate if we reformulate in terms of the material time, then it's just linear response theory. So all this highly nonlinear stuff is suddenly becoming an example of linear response theory in this way of thinking. And I'm not sure he himself realized how clever this idea is. But some years ago, Physics Today, they wrote a paper about some of our results. And they asked me, we have a company policy that we always mention people's first names and last names. What is his first name? And I said, I have no idea. I never met the man. And as far as I know,
the last name is his first name.
Maybe, but that's what the Physics Today said. And I had no idea. And then I wrote to George Scherer and Greg McKenna, and they said, why don't you write to him yourself? Apparently, he was still alive. I did not know. So I wrote to him, and all this within 6 hours, I got a name, Untitled. You probably can't read it. And I told this story then to Itamar, and he said, oh, these fools, because it's the name of a village in southern India where he comes from. But Untitled, Narayanaswamy, that's the O. Then, of course, I went to Google to see whether there's any place where it's mentioned. And there was one place where they used, he never used his first name. And that was, of course, in the US patent database, where you have to give your first and last name. Anyway, he wrote to me he was happy with some of the results I will show later. And the question is, how do we use this in predictive purposes? And then we, like 10 years ago, developed a simplified version of his approach, which we call single parameter aging. And I won't bother you too much with the details, but I think you can see the mathematics is not extremely complicated. But we start here, where this depends on the jump, and this function is universal. Take the time derivative, then we get phi prime of this one times the time derivative here. But because this function is universal, then the material time will be a universal function of the R. So this one is universal. And now we have this differential equation. This we call the aging rate. This is how fast the clock ticks. And then you can basically go. The next step is that we assume that the aging rate depends exponentially on the measured quantity. It depends exponentially on the measured quantity, and the measured quantity is written in a complicated way here. This is the normalized relaxation function. You multiply by the magnitude. This is unnormalized. So
what's the exponent coming from? I didn't understand.
It's not an exponent. This is just an empirical parameter.
Why the exponential function?
The justification is that this is controlled by energy barriers, so you will have an exponential. But this is our assumption that we are making.
An input.
This is our assumption. And the bottom line is that if you go through the math, which is not complicated, you can calculate one nonlinear jump from another one. And you don't have to do any fitting with any stretch exponential or anything. You can just directly calculate. And the equation is given here. If we have one jump, R1 of T1, then we can calculate the inverse of how the second time depends on, for the second jump, how it depends on R from this equation. What gamma is? We call this the aging rate because that's how fast the clock ticks. So we have tested this for the data that I showed you on the glycerol data. So this is the jump we use as input, and from that we can calculate the other jumps. There's only one free parameter in this calculation, but we can actually also get that from two jumps without any free parameters. So it seems to work, this simplified version of the Narayanan-Swamy formalism. This is actually the paper by Dyre and collaborators. She was a postdoc with us during the pandemic, but she managed to sneak into the lab and had the experiment going all through the pandemic. This is the paper that Physics Today wrote about. And what she did was to have some extremely small jumps. So we have very good temperature control with a home belt setup with a Peltier element. And again, it's not rocket science at the end of the day. But she did, actually, she went down to 2 millikelvin, but we reported 10 millikelvin jumps. And of course, eventually linear response theory works, right? So you can see that the normalized functions, they collapse here. But from that, we can calculate the nonlinear ones from the equations I showed you previously. It doesn't have to be two nonlinear. One can be linear, one can be nonlinear. So the predictions are given by the dashed curves here for 1, 2, and 3 Kelvin jumps. There's some deviation here, which Christine speculates that this may be actually an error of ours. But anyway, it works pretty well, predicting the nonlinear jumps. So we wanted to go one step further, because once you have you can do any temperature perturbation. It doesn't have to be a jump once you know the linear response theory. So we wanted to make a sinusoidal. So the red curve is the temperature variation here, 3 Kelvin sinusoidal. And this is a roughly 12 hours period of here. And the black curve is the predicted one from the linear experiments. And the turquoise is the measured one, which fits nicely. And again, there are no fitting parameters in this prediction. what really impressed me was the fact, if you look at this, the first one here is not identical to the second one. And that's because we have, of course, initial, what's it called, you know. Yeah, so we start here actually at t equals 0, right? So it's not a steady state until a few cycles later. And even the deviation here is reproduced by the theory. Okay. In the same paper, we also tried to see whether we could confirm single parameter aging in computer simulations, and it's the standard Korb-Andersen binary Lennard-Jones model. This was done by Said, at the time, a PhD student of ours from Iran. And here we consider jumps to a relatively high temperature, 0.6. Nowadays we do them to lower temperatures. And the quantity that we study is the potential energy. So you need a lot of simulations to get good statistics because it's it's just one number, a global quantity. These are the normalized relaxation functions as function of log time. Now, the fortunate thing with the computer simulations is that we can use the fluctuation dissipation theorem, so we don't have to measure the linear response. We can use just calculate it from the potential energy time autocorrelation function. So we know the linear response, which is the black curve, and from that we can then predict the other ones, and you can see maybe the dashed curves are the predictions of dashed colored curves, and it seems to work okay. Right. So more recent experiments, I won't go into a great detail with this, but monoalcohols tend to behave differently from the ordinary van der Waals leak, which we usually study. So we wanted to see whether single parameter aging also works for monoalcohols, and the answer is yes. Here are some of two jumps to the same temperature. Two final temperatures and many different jumps. What we did in this case was we took the nonlinear one and then we predicted the linear response from that, which should be unique. And so this collapse here are the predicted linear response at the different final temperatures. So they collapse pretty well, all the data here, again confirming this, this approach.
But it doesn't change the fact that you, despite this, you have many slow processes, and it doesn't change the fact that you have a single parameter.
It's a good question. I mean, here we. You mean you're thinking about the Debye process, or?
Yeah.
No, it has a very weak thermal signal in many respects, the Debye process. So that's not a problem. Here we measure. Actually, he ended taking the imaginary part, but usually we take the real part, and it's basically a measure of the density in the capacitor. So the Debye process plays no role. But we were not sure it was going to work. That's why we did this.
So from these simulations or experiments, can you reconstruct within your approximations how the material time depends on time and how this is changing by positive and negative delta T? I don't have any intuition. Does time stretch or does it accelerate? What is it?
There will be some data later on this. Thank you. So now the question is, what is this material time? This is Ian Douglas, who was a postdoc with us, coming from Peter Harrowell's group in Australia. So we published a paper which is where we discussed this, called Distance as Time in Physical Aging, and the idea is the following. So I went back to some, back in the 90s, I thought about a lot, how can we explain time-temperature superposition that Jorge mentioned. So if you have a log frequency scale and measure a mechanical response or a dielectric response, you see some curve, and then if you lower your temperature as seen from you, then it will move to the left at lower temperatures, but very often you see exactly the same curve, same shape. And we also can do this for different quantities, and they move together. Anyway, this is called time-temperature superposition, so it looks like everything is just being more slow, but otherwise the same somehow. And my idea was at the time that, how do we decorrelate by moving in configuration space? It's just by moving away from where we started, right? So an autocorrelation function is simply, my idea was it depends on how far we have moved away. If we move far away, then we have a zero correlation. So the obvious thing is to say that an autocorrelation is controlled by a function of the distance you have moved away, and what happens at lower temperatures is that you just move more slowly, but otherwise the same geometric autocorrelation function. That was the idea. I tried 5 different journals, and I gave up getting this published. But fortunately, the archive was invented at the time, so I put it on the archive and forgot about it. But now we can use this idea maybe to understand physical aging, which is out of equilibrium. So the idea is basically that there's some distance measure, and these are the coordinates of one state point in configuration space, 3n dimensional. There's some distance measure, and I will come back to what's the right distance measure, because it's not the mean square displacement because of the vibrations, they ruin it. So you need to have some other, and once you know this distance, the idea is that that's what controls the change in material time, right? And the question is, how can we test that? And I just want to mention this briefly, that if you assume this, then it's fairly straightforward to show that there's an interesting geometric reversibility, even though everything is irreversible. And basically, here we have 0.1, and then a time later we have 0.2, and then we have 0.3. So time is moving in this direction. And in order for this to be consistent with equilibrium, we have to have the property that if we know this distance, and if we know this distance, then we also know this distance, right? Because if we know this distance, we know this, the change in material time from here to here. If we know this distance, we know the change in material time. And if you add these two changes, you have to get the correct change from 3 to 1. Okay, so I call this unique triangle property. So the triangle of any 3 points have to have the property that if you know 2 lengths of the triangle, you know the third one, which is a strange geometric property. But that's how it has to be if this is going to work. And then if you continue this reasoning, then you can show that this is actually a symmetric function, which is not trivial. It's a simple derivation. It's in our paper. I tried to reconstruct it this morning, so I couldn't reconstruct my own argument, so I won't go. But you can read it in the paper. You introduce a 4th time and so on. Anyway, so now I want to connect this to what Jorge Kurchan and Leticia Culiandolo made many years ago in this pioneering paper, which you didn't talk that much about. This is called the triangular relation, and C is an autocorrelation function between 2 times. If you know the autocorrelation function between time 1 and 2, and 2 and 3, then you know also the one between time 1 and 3. And this is the basis for the time reparametrization invariance. I think that this triangular relation, 100 years from now, when we are all gone, will still be standing. I think this is really a very, very important contribution to the field. And what they also showed in the paper in 94 was that this is actually a symmetric function, which is, I'm not sure I still understand the proof. You refer to some group theory and so on, but they showed that this is a symmetric function. And remember that we are talking about out of equilibrium irreversible processes. It's not at all obvious it's symmetrical. Now, so I think you can see that this and the Narayana are really almost the same thing, but they come from completely different sides. We're talking about relatively small jumps, still highly nonlinear temperature jumps. If you read that paper, basically they went from infinite temperature to 0 temperature, basically. That's my understanding. I've tried to read it many times, I should say, and I'm not, maybe I should try another time. I don't understand all the details in the paper.
Let me say very quickly, the only thing you have to see is that, no, just very quickly, the only thing you have to see, and it's very easy, is that F is an associative function, because you consider 4 points and then you do it 2 ways and you realize that. And then you go to the book of Hazel-Winkel, who classifies all associative functions, and you get everything.
Okay. Yeah, so we come from we're sort of reducing everything to linear response theory by replacing time with material time. Jorge and Leticia, they are looking at quench from infinite temperature to 0 temperature. They never refer to thermal equilibrium in this, as I understand it. And nevertheless, it's the same stories somehow. It's coming together, I think. So that was fun to slowly realize. What more? We have some, we can simulate this, and now we come back to what is the correct distance measure. And the one we used here is the mean square displacement between the inherent states. So you quench to a minimum, and some time later on your path you also quench to a minimum, and then you can calculate the mean square distance between the two minima, and use this as distance measure. Then you get rid of the vibrations. This is done by Ian Douglas. So we made it's Cobb Andersen, made a slow heating and fast cooling, and also another protocol just to do something. And then we plotted, for all these many points generated, we plotted the distance between point 1 and 2, and the x-axis, and the distance between 2 and 3 on the y-axis, and then the color gives the distance between 1 and 3. But you cannot really see whether this one is uniquely determined, but you can see that on the next figure. This is the coefficient of variation. So for a given point here, this one should be a unique function of these two, and indeed the variations are very small. So we have confirmed this property that if you know two lengths of the triangle, you know the third one to a very good approximation. Another way of plotting this is to look at, here we have, we plot different curves for a given value of, let me see. So this is D13 as function of D12 for a given value of D23 distance. And then we have equilibrium data and we have aging data, and they all collapse on the same curve. So this confirms that it's the same movie going on, whether we are in equilibrium or whether we are aging. We are on the same curve. The relation between the distances for a given 2, 3 is exactly the same in equilibrium and out of equilibrium. It turns out that was not the correct distance measure to collapse all data, but it worked pretty well. And the question really is, what is the correct distance measure if the material time change is simply a function of how far we have moved? And we tried different things, and Camille Scalier suggested to us, why don't you use the inherent harmonic mean? And the harmonic has nothing to do with vibrations. This just means the 1 over n sum is called the harmonic sum. So the charm with this equation is that it emphasizes the slowly moving particles between two states. If you have moved a little small distance, you have a large contribution. So the slow particles are the most important in this distance measure. And that's the one we found to be best to collapse our data. These are quite extensive computer simulations going to this temperature, 0.45, and we're jumping from 55 and from 50 and from 40. So this one, this blue curve is the normalized relaxation function for the jump from 0.4 to 0.45 for the potential energy. And we didn't have one from 35 because we couldn't equilibrate at 35. And these blue curves are the normalized relaxation functions, and they collapse pretty well if we use this distance measure. There is a mathematical inconsistency in the distance measure, but I don't think it's a serious problem. If you interchange two identical particles, you will get a contribution to this one, but you have no relaxation because they are identical. But I don't think this is a serious problem. Okay, so some more recent work was done with a group in Darmstadt. Thomas Blokovic has a group doing dynamic light scattering. And they spent 8 years to get their equipment to work, because you get a very, very weak signal if you go into a molecular liquid with a light source. If you have particles, you're fine, but if you just have a molecular liquid, it's difficult. And what we would like to measure is the ensemble average time autocorrelation function during aging. Usually in equilibrium in dynamic light scattering, you simply get good statistics by having a moving time window like this. But you cannot do that during aging because things are changing, so you need to do an ensemble average. And the solution is to use a camera, which Luca is also doing some of his experiments. So we come in with a laser here and look at the scattered light and take 20 or 10 pictures per second and do that for 1 or 2 days. You get a lot of data. And then the individual pixels will have an intensity which looks like this, and you can then work out the ensemble average time autocorrelation function. So this is how it looks in equilibrium, and this is a jump from a high temperature and 2 Kelvin down. So we end up at, we start here, and we end up here. Okay. And now we can actually determine the material time from the time autocorrelation function of the scattered light. So basically we assume this fundamental thing that the time autocorrelation function controls the change in material time. And then we find some level, I think 0.3 for the normalized. Here's the time autocorrelation function, and once it reaches this level, we say we have 1 unit of material time. And then we start all over at a new time autocorrelation function starting here, and it decays to here. That's 2 units of material time, and so on. In this way, we can determine the material time as function of actual time here. So these are for some jumps, and they, of course, they jump to the temperature. Eventually, they will end up following the green line of the equilibrium temperature. I don't want to go through all the curves here. Here are some normalized relaxation functions for the light scattering itself, and here for a dielectric signal for different jumps, and as function of time, and they should then collapse if we do it as function of material time, and it seems to work pretty well. This is actually the first time that the material time has ever been measured, because it's really very demanding to do this. But coming back to the title, reversibility. Now, remember that the whole idea is to convert this nonlinear phenomenon into a linear response phenomenon. And linear response theory has time, is equilibrium and has time reversal invariance. So it's rather obvious, once you know the material time, to see whether you also have a reversibility in the fluctuations of the material time, right? So I looked up in the literature, how do we check this? And there's something called the visibility graph method. I don't know whether you heard about it. How many heard about visibility graph? But that's what I could find, and we used that method. We also made some with the Fourier transforms, but basically you look ahead on the signals, and then you make the statistics of how many mountains you can see ahead on the one-dimensional time axis, and then you look to the past and make the same statistics and see whether or not they are the same. Okay, it's made for discrete processes, but we use that, and the conclusion is that the blue ones are the intensity in the actual time, And the red ones are the same signal plotted as function of material time. So this is the same signal, but as function of different time measures. And when we do it as function of material time, we come down to this limit, which is called reversibility limit. It has to do with the finite statistics and so on. And we also did some moving Fourier transforms, and again, the red ones are the material time, and it looks like it doesn't change, whereas this clearly irreversible. So we concluded that aging has some element of reversibility. And then we tried to find some counterexamples, and I won't go through this. First we took laponite, which I think Luca has also worked a lot on. But it seemed to work also there. Then we took a curing epoxy, where it cross-links covalently. Even there, it seems to be reversibly aging. And this one was a computer simulation, yeah. Okay, so the points that we made in this paper was that we can measure the material time. When we use this as time variable, we cannot really distinguish past and future, which is, and our findings are consistent with time reparameterization invariance. And finally, even the chemically aging system showed reversibility, which is I still don't understand. So there was a lot of noise about this. Of course, if you have a paper about reversibility and time, there's a lot of internet attention and so on. So the final slide I will show is this one. Some recent simulations done by Aude, which Jorge also mentioned briefly, where we tried to see whether this whole framework works in large up-jumps, because there are good indications also from Ludovic and Camille that you have growing islands and whatnot. It shouldn't really work for large up-jumps. This is the Korb-Andersen model, and I won't go through all the details, but we measure the potential energy time autocorrelation function as function of time here, and then we use that to define the material time, and then it collapses nicely, even for this large up-jump. So I'm sorry, there's actually an error here. It should be 40. This should be 43. This is an error. So this is the small up jump, and this is the large one. And then we tried different quantities, and also chi4, which is the favorite quantity for measuring dynamic heterogeneity. But you can see that it's not fantastic collapse, and I would have loved it to work, because dynamic heterogeneity is completely against the idea of a universal time, because you would expect fast and slow regions. So we don't have any very clear conclusions. Let me just summarize the paper here. The material time concept linearizes a highly nonlinear phenomenon. Of course, you can say our jumps are small, but it's still highly nonlinear by any mathematical definition. This simplification, called single parameter aging, allows you to calculate one nonlinear curve from another, or one nonlinear from the linear response, or if you want the linear from the nonlinear, whatever. And it seems to work. So in this way of thinking, everything is inherited from equilibrium. And this is where we are completely different from what Jorge is doing with the triangular relation. But that's my way of thinking. We are close to equilibrium. And that's why we can linearize and so on and so forth. So what are the open questions? The triangular relation is, it's not known when it works and not works. This I know because I read a review by Giulio Biroli and Jean-Philippe Bouchot, where they stated this at the end, that it's not known. And we would really like to know when does this triangular relation apply. It's not, probably not 100% universal. And what about dynamic heterogeneities? Do we need local clocks? I'm not sure that's the case, but we're looking into that now, and it requires a lot of computer simulations. I'm aware that Castillo and others did that 15 years ago, but we have much faster computer nowadays, so we should we should look into that problem. And with these words, I want to say thank you for your attention.
Okay, questions?
I'd like to raise something subtle, so give me a minute, okay? So my impression was that I understood Jorge's lecture in the following way. I know from many years that if you do Monte Carlo simulations or molecular dynamics, it's the same. Now, I'm happy to say, let's look at Monte Carlo. I have steps. I can do the steps quickly or slowly, and it doesn't matter, and then I understand what Jorge is saying. However, when you do a T-jump, you're no longer protected by Metropolis Einstein. So it works, I think, in your case, only because the temperature is almost the same as the one that you started with, and therefore you have almost Metropolis Einstein protection, and this is why you see to the accuracy of the plot the things fall on each other nicely. But when you do a large temperature jump, forget it. This is no longer true because you're not going to be protected by Metropolis Einstein, and therefore the whole idea falls and disappears.
Yeah, in my understanding, but I'm thinking about this now, it's not important that you have the metropolis, because the important is that you have detailed balance, and this you can have even...
But that's the same.
No, because you can be far from equilibrium. You can still
But
have
that's
detailed
the
balance.
issue.
If you're quenching to extremely low temperature, you can, your rates can obey detailed balance, even if you are extremely far from equilibrium.
Why?
And well, I mean, usually you would assume that you have detailed balance in a system like this.
If you're not in equilibrium, I'm not sure. Anyway, so there's a subtle issue here that you may want to clarify, maybe you want to clarify, I don't know.
But as I said already, I think the fascination is that we're coming from completely different directions in the understanding here. Would you, okay.
So Jeppe, can you show the graph of the Chi4 data that you had? Yeah, so I mean, you went by this a little bit. I mean, so from these, when you plot on the right-hand side, you're plotting against material time.
Yeah,
right?
the difference in material time.
And you did nothing to the y-axis.
We tried so many things.
Yeah, I mean, from just looking at it, except for the extreme end, it looks as though this is collapsing the data reasonably well. Is that the conclusion you're drawing, or are you looking at where the departures are and focusing on that? So what is your message from this figure? And in particular, I want to understand what happened to the amplitudes of these susceptibilities.
I mean, that's a good question, and I have actually forgotten, to be honest, because we tried many different things, and it rings a bell that this may be normalized by the maximum, yeah. But it's not indicated on the figure that Aude made.
Two. Yeah. So no. I agree. And this is something that related to Ludo's question before. If you are looking at a 4-point function, simple renormalized stretching of time should not. But what I want to say, nobody really worked a lot on this. So I cannot say exactly, but it is what you would expect, because precisely one is the fluctuation of the other. No, the 4-point function is a fluctuation, and fluctuations are there precisely because there is the reparametrization softness. So in fact, the dynamical heterogeneities are not an exception, are the telltale sign of this softness. This is. But you're right, I don't know, I don't have the right calculation, but it's not as simple. It could be that Jeppe did something to the y-axis, but it could be that you have to in a 4-point function.
It would be nice if you can work out what...
Sure, and I think that it would be nice to rederive the assumptions that Giulio did with Ladieu and Jean-Philippe, and see that they are nothing but reparametrization. I am completely convinced, but it's work.
I have questions about the experiments. So you showed us some very preliminary Laponite data. Yeah. So now lapamide, actually, at least experimentally, we see two different aging regimes. There's an initial exponential aging, and then there is a power law simple aging. So I was just wondering if you have tried to look at different. Where exactly did you acquire the data?
I think this is to the long-time aging.
Okay,
but of
so
course
that's the power law regime.
Yeah, it never equilibrates.
It doesn't, yes.
Yeah.
I have another question, and this is something we've been struggling with. How do you do a temperature jump in a DLS measurement? Because I'm guessing you're using a water circulating cooling mechanism, right? Yeah. We can do ramps, but rates are so difficult.
Yes.
I couldn't see what the final and initial temperatures were, but...
Yeah, it takes some seconds to equilibrate, and I don't remember the details because the experiments were done in Germany, so not in our lab, the light scattering experiments. But as I mentioned, it took them almost a decade to get this to work, and they also had all kinds of issues with the temperature control and make some compensations, and it's really complicated to get it to work. Yeah.
Thank you.
Okay.
I wanted to return to the point of large temperature jumps. Jeppe knows everything I'm going to say, but I think it might be relevant for some other people in that we absolutely know from experiments and simulations that if you take a big temperature jump, the intermediate states do not look anything like equilibrium states. And so it's not a surprise that methods that have that assumption embedded in them are going to fail for a big enough jump. For example, if you start with a highly stable material and you make a big temperature jump up, you will get bubbles of mobile material, and they can grow in experiments up to sizes of microns before they chew up all the immobile material. There are no equilibrium states that have bubbles of highly mobile material surrounded by a network of really immobile material. I mean, no equilibrium states. An infinitesimally small fraction of equilibrium states have this character, and so.
Yeah, I think that's a good and important point, but we still need to understand whether or not the triangular relation applies in these cases.
How could it?
It was not designed.
So I'm trying to put in the same framework what you said and what Jorge was saying and to draw analogies. I think basically what you're doing is that you're, as you say, you're nonlinear, but nonetheless you're close enough to linear response that you can use an effective linear response theory. And there are other problems, we know, for instance, in active matter, when you can describe the active system as an effective equilibrium system, or, lots of non-equilibrium stuff. Mm-hmm. But when you are very far from equilibrium and linearity, you have to use something else. But what it seems is that there are nonetheless general principles that seem to be at work and at non-trivial in your effective linear description and in what Jorge is doing. Mm-hmm. And I think trying to understand what are those general principles. What I have in mind, for instance, was the macroscopic fluctuation theory that describes some non-equilibrium systems, even very far from equilibrium, but with a whole unifying framework that can be used close and far from equilibrium. Mm-hmm. So there must be some organizing principles that are at work both very far or close, I would say, to linearity in those problems.
That's a great open thing to look into in the future, this question you're raising here. And I would love to understand that. Can I just make one comment about this? Because these are very small jumps, apparently, 1%. But if you go continuously through the glass transition, as you do in a factory when you produce a glass, then actually this whole formalism works very well of the Narayanaswamy formalism. And it's been used in industry since the 1980s routinely. You can meet many people who are using it every day. because the falling out of equilibrium takes place in a rather narrow temperature region if you have just a continuous cooling. So it's actually much more useful than it appears when I talk about temperature jumps. Okay.
So if it's a quick, just one last question, and then we go to the last speaker.
Yeah. No, I mean, I guess, going back to the tool, Narayan Swami, the idea was that the system at any instant was going to experience the dynamic of the instantaneous temperature, right? I mean, that's sort of, yeah. And I guess everything you've shown is saying that that idea can be formulated better, still sticking to that assumption, and then you have a powerful way of describing a lot of out of equilibrium. But as Mark said, if you go sufficiently far from equilibrium, that the dynamics, the instantaneous dynamics is very different from equilibrium dynamics, then all hope is lost.
Yeah. Yeah? And that's also what we saw in old simulations, that it doesn't really collapse.
Okay. But the first regime is a very interesting regime to do a lot of things. Yeah. Okay, great. Thanks.
Okay, so let's thank our speaker once more. And our last speaker, I think this is the last speaker, right? And then we will, is Anael Lemaitre. And quoting you, he's going to talk about what he's going to talk about. So. Can you connect? Hmm? 35 minutes with the question. I will just stand up when we are at 30 minutes. Okay. Then we are flexible.
Let me just get my...
Oh, maybe it's working. Okay. Okay. So it was a very interesting conference. So I learned a lot. So I'm very grateful to the organizers for the opportunity to attend. Yeah, that was really very diverse and interesting. I'll talk, the connection with the previous talk is the word aging, and the expectation I initially had that by looking at a system that my experimental colleagues were interested in, the hope I had to learn something about structural aging. But nature has its quirks and decided otherwise. So, maybe it's not the place where I need to explain what is soft matter, but I'm going to talk about something we didn't mention, which is thixotropy. And thixotropy is the fact that some materials have mechanical properties that evolve in time. So typically, ketchup is an example. You take a bottle and you shake it very strongly, and if you shake it for a little while, it will flow, and then it will stop. And so the fact that the viscosity of some material will depend on time. The motivation of my experimental colleagues and the lab where I am in is cement. And I think I want to really attract your attention on that. I mean, that's a soft material which is responsible for 8% of CO2 emission worldwide. And just to give you an idea, the photovoltaic production helps with 1.7%, maybe that was a few years ago. Aviation fuel emissions we hear a lot about is 2.5%, and cement is 8%. So it's something absolutely massive. There are lots of interest in physics on, I don't know, for example, photovoltaics. I mean, tremendous funding for photovoltaics, which is this. But if you help just a bit to reduce the CO2 emission of cement, I mean, we have an immense leverage because cement is a single material. So there is a huge leverage in soft matter to help reduce CO2 emission and address that. And the reason why it's 8%, and it's 10% of worldwide industrial water consumption, which is another tremendous environmental issue. And the reason is that the main way to make cement is to use
a limestone that you heat, and simply it's chemistry. So you just burn limestone and you have CaO plus CO2, and just by the chemical balance, you see that for 1 ton of cement, you produce 0.7, 0.8 tons of CO2. And that's not counting the heat. So there are alternative ways. There are ways there are ways for industry to change that. And the better example of that is the Roman Pantheon. And if you have not seen this is something that was built in just the 2nd century. And there is a dome in the Roman Pantheon, and this dome is the oldest dome made of cement. And it's not made with clinker that I just talked about. It's not a cement which is made from a limestone which is burnt. It's a cement which is made from pozzolaning, so from volcanic ashes. And so you can also make cement from volcanic ashes. The problem is the chemical reaction is not the same. It does not consume water. It consumes CO2, which is absolutely astounding. But the problem is because you cannot process, you cannot put all this water inside, you need to, it's much thicker. So if you have Roman slaves, you have people who can put it by hand in the right place. And if you want to flow it, as we do currently, you cannot. So you can replace part of the clinker with silicates. But the industry is struggling to understand how to do that. And that's where we can help. So it's also, there is new technologies like 3D printing. And you see that basically you can print layers and layers of cement. But to do that, you need to make sure that the lower layers can sustain the upper layers. And so you need to have a control of how the properties of this material will evolve in time. And it's a material that does show aging. And so if you take a cement paste and you just put it at rest, and you will see that the modulus ages logarithmically, the yield stress ages logarithmically. And if you read in textbooks on thixotropy and aging, I mean, there are many other materials where you have this. Rheological textbooks basically have been very much inspired by all the experiments that people have done on colloids and the analogy between colloids and glasses. And so if you read in textbooks, people tell you that this thixotropy and aging has a structural origin. It's just the same thing as we saw before with molecular glasses, and maybe it's because the structure there is some slowing down of the aging dynamics. Just another thing to continue on this material, that when you put, of course, you know, cement will eventually react and become a solid, but this reaction can take time, can be delayed. And there is, when you think about how to process the soft material, you are interested in what happens at the early, what is called the young age, so before this reaction takes place. And so what happens here is that when you mix cement with water, you really have a release of minerals, and then you have a paste that you can manipulate for a while. And I mean, that's important because if a truck is stuck in traffic jam, you don't want to end up with a stone, right? So you need that. So that led some colleagues of mine, so to construct a model of cement, which is essentially colloidal. So we have here microspheres of silica, and the silica is produced by the Stober synthesis. It's extremely highly controlled. So we have very highly monodispersed spheres of silica, and they are in a fluid which is can be water or glycerol, and what's important is that they are ions. It's an ionic suspension. And the packing fraction, typical packing fractions are 30 to 40%. And what is amazing is that at 40, 30%, you have a yield stress. And it might be surprising because you're much below the random close packing, but you still have developed a yield stress. So that's typically the kind of data we can get. So we have rheometry protocols, and so you can measure here the Young's modulus of the system. So you have here systems of microspheres of different diameters, and you look at the shear modulus as a function of time, and you see, so there is a dependence on the size of the particle, and you have this logarithmic aging. You take the yield stress also, so basically what people do is that they pre-shear the system and then they do very small oscillation to get to the modulus, and at some point they ramp up the stress and then they get to the yield stress, and so you see an evolution of the G prime and the yield stress. So yeah, so when we started looking at that, everything, the interpretation was based on the glass analogy. If you look, of course, we have all these colloidal systems that are model glass, and they are very interested for that because they can address questions about glasses. And so we have also there is also the idea, for example, that you produce clusters, or something is growing in space. And so when you look at there is also in dilute systems the idea that you might grow clusters, or maybe you might grow some by diffusion limited aggregation. Yeah. Yeah. Yeah, okay, so we ramp up, say, rapidly compared to, so you're right. In fact, if you look the curve, it's to this one? Yeah, that's the one, yeah. So you're right, but there is well, it's quite clean, in fact. You start to ramp up the stress rather, yeah, and there is a pretty well measured, yeah, it's pretty clear, yeah. So, okay, so let's look at structural aging. So we take our suspension, we put it in a confocal microscope. So it's a bit difficult because it's opaque, so we need to reduce the index contrast to be able to see the particles. So for that we had glycerol, and so that we managed to image. So yeah, it works again. Okay, so you look at, so that's a photograph. That's the reconstruction of the particle position. This is the G prime. That's the time when we take this picture. And that's a later time.
Just one second. Yeah. So just a clarification. So you said that this is in glycerol,
there is a mix of water and glycerol.
Okay,
yeah.
But then that would change the interparticle interactions from your...
Exactly, and it reduces the attractive forces. Because the attractive forces are van der Waals, and so it makes it less adhesive. Okay? And I'll come back to this point a bit later. So now what you see that 1 minute, 5 minutes, and so you see some particles are here, but what happens is that you have a bit of photo bleaching, and so you lose track of some particles. But the particles that you can keep track of don't move. And so you can look at the later time, and again, the particles you can keep track of over 10 minutes, they don't move. But the modulus ages. So now you have something which is not what we hope to find, but which is that we have aging and we have no structural dynamics. So what could it come from? So it's, in fact, the only thing it can come from is that, so basically you have a microstructure that freezes in seconds because, yeah.
Anael, can I just ask about the coordinates that you plot on the right? Is this from a 2D analysis or a 3D analysis?
Oh, that's, so we have a cut which is, say, a few particles, 10 particle layers away from the plane, the bottom plane. Mm-hmm. And so we get that's a 2D cut. Mm-hmm. And that's the reconstructed.
So you take the coordinates from a 2D optically defined plane?
Yes.
Okay. Okay, all right. Thank you.
Yeah.
Thank you.
So the point is that the interactions between particles, yeah, sorry, oh, there is. Yeah,
so these are also not density matched, right? So they
absolutely.
Okay.
They are not density matched, and that's why it's.
You do have cesium chloride, and that would, I think, go a long way.
But that's exactly the point. So it's not density matched, and it's stable at 30%.
it is stable, it is under gravity, it no longer settles beyond 30%.
It does not settle, and we'll see. I mean, it doesn't settle because it creates adhesive contacts very rapidly. Okay. And so the point is that we have all, and in this literature there is this idea that if you don't have, there is this notion of stable, I mean, the fact that if you have adhesive forces, you lose stability in a certain way. But it's the opposite. Here, in fact, you maintain homogeneity because you have adhesive forces, all right? So the point is that, of course, the interactions between our particles are controlled by the DLVO potentials. So you have van der Waals attractions, you have the repulsion, which is due to the charges. This repulsion is screened, and when you have ions, you strongly screen the Coulombic. So these particles are charged, right? So silica in water is charged. So they repel each other. But if you add ion, if you have an ionic suspensions, and that's really something very general in nature. You have many mineral suspensions in which you have ions. And when you have when you have mineral suspensions, they often have an index contrast. The index contrast is essential to get the van der Waals attraction. And the ionic, the presence of ion will screen the Coulomb repulsion. And in that case, you have a situation. So the generic picture is this. But in fact, now we can take our system, we measure the charges of our particles. I'm sorry, there are movies that will not show up. But basically, if we reconstruct the DLVO potential, we have, depending on the ionic strengths of the suspension, we can very easily and for very reasonable values of the ionic strengths, we're in a situation where particles, basically there is no, the general idea is that when you have the LVO potential, you have a primary minimum where particles are in contact, you have a secondary minimum, and normally if you want to say so-called stabilized suspension, you try to have this barrier and to play here. But the point is that when you have ions and significant index contrast, basically this barrier will totally disappear. And in that case, you are in system which essentially you are adhesive. And so even in adhesive suspensions, people expect structural evolution. So in our case, we have adhesive suspensions where there is a kind of gelation dynamics, but yeah, there is a form of gelation dynamics, but the gelation dynamics occurs in a dense system. It's not in a, here you have gelation in dilute system. When you have gelation in dense system, you don't see so much motion because each particle is close to another one. So you can gel by a very rapid formation of a dense network. And so you can freeze the microstructure within seconds, and then structurally nothing else happens. Now, we see aging on the modulus, and the only thing that can age are the contacts. And so there is a beautiful experiment that was done by Pontinine first, and Eric first created the technique where they take colloidal particles, and using optical tweezers, they manipulate the particles, and they form a rod of particles. And the first thing which is amazing is so you have colloidal particles that stick together. And what Eric first showed, and Pontinine first showed, is that when you take this, so they do a 3-point bending test. So you hold the end particles, you grab the central particle, you pull on your rod, and you see that, you pull on this particle, and you see something that is bending like a rod. The fact that it's bending tells you that the contact resists rolling. Okay, so if the contacts were rolling, you would see, if you take a string and you do that, you see a triangle. If you see a rod-like shape, it means that all the contacts are resisting rolling. And so that was something that Pontinine at first showed. And so basically our idea was that maybe this rolling, this stiffness, this flexural stiffness might depend on time. So now so the picture is that we rapidly gel, but we have a system where the properties of contact will vary with time. And so typically, when you do this test, you have the deflection. Here you measure the force. And so you measure the force, and so you will increasingly bend your system. From the force deflection, you measure a modulus, and at some point the system will break. So now you see here the force deflection curves measured at different time, and so we do see that there is an evolution of the stiffness of the contact. And so now we extract the bending rigidity of contacts from different experiments with different ionic forces, different numbers of particles. And so you see that generically we can construct, we measure an evolution of the bending stiffness as a function of time, right? So the contacts stiffen with time. Okay, so we can go through the theory. The only interest going through the theory here, we are looking at the elastic interaction between two particles. Essentially, the thing to keep in mind is that when you have two particles in contact, there is a small area of contact. And what determines the modulus is essentially this area. It's just a geometric problem where you have two particles in contact on a facet. And so the whole elastic response is determined by the size of the facet. So if you have an evolution of the modulus, you expect that this area of contact will grow. It grows because of the evolution of the adhesive energy. And the point is that once you know that, you know how the bending modulus varies with the energy, the contact energy, and you know how it varies with the particle size. And the point is that you can basically get a scaling of how these bending modulus depend on particle size. Yes?
Yeah, I didn't understand qualitatively where the bending modulus comes from. So,
well, the particles are adhesive, and this edge of the point is that the edge of the contact is pinned. And so that then it resists rolling. So because you have a pinning of the edge. So this is fixed.
So it's pinned. It's not the same as solid friction, right?
Solid friction is not the same. No, it's not exactly the same. And actually, it's a pinning problem, and the opening is in fact related to fracture, and it will come. Yeah. So the only reason why we do that is because we cannot measure this on many particle sizes. We can measure that on one particle size. Yeah.
Just to clarify this point, so the picture you have is that when you have these things stuck, at any point in the interface, you have elastic response, so you're just scaling with the area. The overall
That's what the contact theory tells you, is that indeed the elastic modulus scales with the area as a function of the area. Yes. So now the interest is that we have basically bending data on one particle size, and we have rheometry data with many different particle sizes. And so the theory tells you that you can rescale all the G prime data as a function of the bending data with some kind of weird exponents here. So the first thing we see that if you take the G prime versus K naught, that's for the radius here is the same in the rheometry and the bending test. So you have a linear relation. For each case, you have a linear relation. So you see that your Young's modulus depends linearly on K naught. So that's a direct evidence that the macroscopic modulus aging is controlled by the stiffness, the evolution of the contact stiffness. You can rescale the data in this way and extract here a function of the density. That's basically, so you can reconstruct the whole G prime data, and then you can play the game to reconstruct the evolution of the shear modulus as a function of time from the data you have at the scale of the contact. So eventually contacts rupture. When you have rupture, rupture occurs usually at the center. I mean, that's rupture point statistics. It occurs at the center. And it tells you that rupture is controlled by a local rolling threshold. Okay, so basically we play the same game. We have rupture. We can construct the rolling threshold. The rolling threshold also depends on time. And we find a relation between the rolling limit and the bending stiffness of contacts. And that's a detail, but we can go through contact theory, and there was some works by Kite and others essentially dealing with this as a pinning problem. And if you deal with this as a pinning problem, you have an adhesion hysteresis, you have the surface energy which varies with time, and when you get that, you can basically back out the relation we get between the bending modulus and the rolling limit. Now, the point is that if you have, so we can play a similar game, so expect that the yield stress is proportional, is controlled by the rolling, the onset of rolling on the contact. Again, this seems to work quite well. So basically, the contact rolling limit will evolve with time and determines the evolution of the yield stress. And now, if you know that the rolling limit of contacts is a square root of the stiffness of the contact, and you have this relation between Kr, I mean the stiffness and the bending limit, and here the macroscopic modulus and the yield stress, then you expect to see, parameterized by time, a relation between the yield stress and the Young's modulus. And this looks like it works pretty well. So basically, in this system, we have a scenario where the aging of the problem is entirely controlled by the evolution of contact. So partial conclusion is we identified a contact aging scenario where the microstructure freezes, contact age, and contact aging determine the macroscopic response. We expect this scenario to have a very large domain of relevance. Most suspensions in nature have optical contrast, so they are strong van der Waals adhesion. They are often ions, and even for moderate ionic strength. So in fact, many suspensions, I know in the labs, many people have been working on model. If you want to work on model glasses, you want systems which are not getting in solid-solid contact. But in nature, most suspensions, many suspensions will be adhesive. And then as soon as you have contacts, as we know, friction, you mentioned friction. We know friction ages with time. And here it's very natural to think that the bending and flexural response and rolling limit of contacts generically age with time. We try with two types we also try with PMMA particles with the same results. It brings up lots of theoretical questions, and I will not talk about that. This is ongoing work. I would like to just add how much time we still have a few minutes. Okay. So I will just mention an evolution of this problem because that's motivated by the experimental problem of cement, where people often use polymers. They introduce polymers, and the first thing they tell you, but when you add these, the theory in the field is that you add polymers that prevent contact. But if you prevent contact, you lose adhesion, and if you lose adhesion, probably you sediment because you have this, it's not density matched. But they don't want it to sediment. So then the point is that we think that even the dosage of polymers that are used, they don't prevent adhesion. And so basically we looked at, and we have studies ongoing in the lab where we looked at some polymers. So here, this is one thing we started to do. And so basically the idea is that we can go fast through that. This is the G prime as a function of polymer dosage. So you add a polymer here, which will, here it's a surfactant which will form a double layer. So the point is that eventually, if you completely cover your particle with double layer, you will prevent formation of contacts. But if it's not fully covered, the particle will find a way, I mean, the double layer will move out, and the particle will find a way to form contacts. And the point is that whenever you form contacts, so essentially here you still have a modulus, you have a region where you start to lose the formation of contact. if you're in the region where you form contact, you continue to see aging, and you continue to see aging, but now it's aging with apparently depends on the dosage, on the presence of the polymer. So if you look at confocal microscopy, you see that if you have here, this is the bare particles, and you add some small amount of polymers, and you continue, the pictures we have is you continue to form contact, and eventually here you see that now you have structural dynamics, and you have structural dynamics because now you prevent the contact formation. So we play the same game. We have much cleaner data because we have a much better optical tweezers now, and so you can see that you continue to have a dependence of the response on polymer, on time. And I just wanted to show, I wanted to show one thing, which is this. So here we see, this is the bending modulus of contacts, depending on the dosage. And so we see the same thing. The contacts at low dosage, you find, you still form contacts. But the time-dependent modulus depends on the dosage. And it turns out that we can understand that by basically the fact that the polymer changes the reaction kinetics of what's happening in the contact. So basically, we see that we have a stiffness of the contact that depends on time, but okay, which with a time scale which depends on the reaction. So the picture we have is that the presence of the polymer might slow down the reaction kinetics. We do not know what is this reaction, but it can be slowed down by the presence of polymers. And that gives us some idea about the nature of this reaction, but which is still an open problem. I will pass. I don't think we need to go through that, except to say that basically we see that the same scalings continue to take place in the presence of polymer, and I think I can stop here. Okay.
Nice talk, Anael. So I'm a little confused because I thought that that contact aging in your first part, like I thought those are like mediated by van der Waals attraction, but you mentioned some covalent bond formation. So
the van der Waals attraction creates the contact, right? It brings particles into contact. Now, what is, okay, I went fast on that. The fact that the polymer can slow down the reaction tells us something. It tells us that this polymer is creating a kind of barrier that might prevent ions to come into. So we think, for example, the calcium ion might play a role. We don't know what is the nature of the reaction. There are some people in the literature tell you form SiO-Si bridges. It could be something else. And we have no clue about what is the correct reaction. But van der Waals brings particles together, and then something happens inside the contact.
Yeah, hi. So I wanted to ask one thing. So as you showed that the structure in your case is frozen, but the structure, the modulus evolves due to the contact aging. So how can we think of this in terms of interparticle potential? So is the interparticle potential between the particles is also becoming stiffer as a function of
Okay,
time?
that's a very good question. So the thing is that the way we think of particles is often that, of colloidal suspensions, is often that we think that there is some interaction potential which is isotropic, which is a function of the distance. What comes out from these experiments is that you need to introduce flexural forces. And it really comes from, you know, there has been some works by Morris and others recently who showed that say years ago we could read that there was colloidal systems below the microns and there was non-colloidal suspension above a micron. And lots of works have started to show that the boundary between colloidal and non-colloidal is not something sharp, because you can start to have that. I mean, Bulbul talked about shear thickening, and so which is caused by the fact that even in non-colloidal system, you have some colloidal repulsion and so an interplay between friction and colloidal forces. So what we see here is that if you are in a colloid at a small scale, you have solid-solid forces. And solid-solid forces are not, do not derive from a potential. You could have friction, you could have, well, here that could derive from the potential, but you need to introduce a potential associated with flexion.
Yeah, to follow up with that, that's really interesting. So is that then responsible for the yield stress being at lower packing fraction? And when I hear this thing, I think network models with bending, stretching. So do you think this might map to the rigidity of networks with bending?
Absolutely. So in fact, for the rigidity, it's pretty clear that the relation between the contact stiffness and the macroscopic modulus is almost evident. I mean, you look at the linear response, if you write your energy only in terms of bending, you immediately see that the G prime should be proportional to the flexural stiffness. This is quite easy to derive. The relation between the yield stress and the rolling limit, this is much more complicated because during yielding, lots of things happen. So that's more complicated.
Hi, Anael. A very interesting talk. I've lots to pester you about afterwards, but for now, a comment on Silke's comment that the volume fraction actually it'll occur at vanishingly small volume fractions. But my question, Anael, was, what do you know about the surface roughness of the particles? Because that's going to be crucial in them not organizing together into mechanically stable tetrahedra and so on, which they don't seem to.
There is clearly, of course they are not perfectly smooth. They are quite smooth, but and certainly the roughness plays a role in the fact that you resist rolling. So I think that's definitely something we think. We don't have much control on the roughness. We did not characterize the roughness with any accuracy, and that could be that's a question. I mean, could it play a role in the aging? I mean, would they have different aging kinetics with particles of different roughness? I have no idea.
You do, but anyway, we can talk.
Yeah, very nice talk, very nice work. Did you try to look under an electron microscope at samples that were aged for different times in order to see whether you pick up something at the particle-particle contact level, like particles sintering, silica dissolved and redeposited?
That's a very good question. Like it's very, we haven't. We know that after a while there might be some damage of the particles. I mean, we for sure they could be used. I mean, if we we expect that if you, for example, shear on the system for a long time, at some point you might create some damage on your particle. We didn't look at that, but I expect indeed that there is some sintering. Well, we can use a high shear rate and we have shown that if you use a high shear rate, you can prepare your system repetitively, at least for a while, in the same initial state. But I agree with you that it's a kind of sintering process in a certain sense, that you form contacts and these contacts age, but you can rupture these contacts with flow. Is it answering your question?
Well, I was more thinking not breaking these contacts and just look at different stages of the aging process, how they look like geometrically, if you can pick up something at the particle-particle contact level.
That's a good idea. We haven't thought about that.
So now, as a told you I really like this work, but now I'm not trying to be nasty, but how is this going to help with the CO2 emissions? No, I mean, what aspect of the emissions reduction are you trying to address?
Well, that's a good question. This plot is already used by cement industry. They just are already, I mean, I'm a bit scared by that, saying that, but you know, the fact that they have, the idea that you have a relation parameterized by time between the shear modulus and the yield stress is something that did not exist, and that now they are thinking about that. They find this square root law at the early age, and then they find something else. And so they are using it to characterize their system.
Right.
And another interest is that by measuring if you know this curve, by measuring the modulus, you have an idea of your yield stress, which for industry is absolutely essential, because you have a non-damage, you can measure the yield stress without damaging. So the thing is that attracts attention from these people. And also the point is that that's why I mentioned the polymers, because they use the polymers, and they had the idea that the models you see that they still use are models where all the interactions are only normal forces. So the realization that it's not normal forces, that you have contact, and that everything is determined by what happens in the contact is a concept that was absent.
Okay.
And it helps them to think about their problem. And basically, the way it works on CO2 is that you need to find additives that basically, if you want to remove water, you need to have better polymers to fluidize the suspensions without completely preventing contact formation, because that's how it will mineralize. So our job is to provide concepts that they can use.
So it's not any kind of process control, but additives. I mean, the what they would want to optimize is what kind of polymer
is the additives.
Yeah.
You know that it's actually amazing that the people who produce the cement do not take responsibility for the rheology. It's the additive people who guarantee you that you will get the right rheology. So,
thank you.
Okay, any other question? Okay, so if not, then let's also speak. Anael, on all the speakers of the session, thank you very much. Thank you.
We have a discussion.
Discussions and final words after the coffee break.